Hello, and welcome to Introduction to Statistics using Excel by me, Dr. Alan Brain. This course provides a taster to statistics using Excel. This course covers many topics and provides a basis for people who should take the field of statistics further. Topics covered are averages, measures, correlation, and simple linear regression. There is no test at the end, and all Excel commands are clearly labelled. Some slides are very text heavy, but there are plenty of examples for us to work through. So why am I using Excel? Excel shows all the commands very easily and removes any complexity. So we'll dive straight in to look at the mean, median, and mode. These are three kinds of averages. The mean is the most commonly used statistic used. This result is obtained by adding several quantities together and then dividing this total by the number of quantities. The mean, or as people most commonly call this, the average. As well as the mean, we'll be looking at median and mode. So rather than just describe these further, we're going to dive straight into Excel to find the average, median, mode for the following. So we got Excel open. Within cell A1 to A9, we would input the following values: 13, 18, 13, 14, 13, 16, 14, 21, and 13. Out of these cells, we're going to calculate the average, median, and mode. As you can tell by the screenshot, we have put in the formula equals average, open bracket A1, colon, A9, close bracket, to calculate the average of all these values. Using a colon is a shortcut to stop us writing A1, comma, A2, comma, etc. As you can tell, the shortcut is very useful and very powerful. So, to calculate the average, just need to put the average of the cells. In the cell next to it, we just put out equals median, and in the final one equals mode. That is all it is to it. Nothing complex, everything is straightforward, because Excel is easy to use. Next, we're going to look at measures. This is a very text-heavy slide, so rather than read it through, I'm going to have you press pause, so rather waste time, and you can review at your own time, and I'll give a 2-second break. But rather than hear my voice read ourselves, we're going to use these straight away in Excel. So, in our first example of using these measurements, we're going to conduct some simple fraud analysis. You ask two students to test a random group of students from the same class 6 times and get their average test score results. You think one of the students did not carry the exercise and fictionalized their results, while another one carried out the exercise as asked. Using the figures displayed, use Excel to find the average, median, mode, range, variance, standard deviation, standard error. Using the figures calculated from above, we should be able to find out which ones are more reliable. So from data 1 and data 2 have the same average as we see from above. But the other statistics associated with the data vary significantly. As data 1 has a much lower variance, standard deviation, standard error, we tend to trust these results rather than those in data 2. Therefore, we could conclude that the data provided by student 2 was most probably fiction. Additionally, since the numbers are not repeated, the modes cannot be calculated. This ENA shown. Now our next step is to look at correlation. Correlation is mainly used to find a relationship between two different sets of numbers. A common task in data analysis is to investigate an association between two variables. A simple way to test this to see if there's any correlation. Correlation tells us whether two variables vary in synchrony. In other words, as one number increases, does the other number increase or decrease? A correlation statistic varies between 1 and -1. +1 means perfect positive correlation. Either both figures increase or decrease together. 0 is no correlation. -1 is perfect negative correlation. As one figure increases, the other decreases, and vice versa. So using the Excel sheet I have pasted it onto this PowerPoint slide, we can see that data 1 and data 2 both increase at the same rate. So therefore they are perfectly correlated. And there's the command in the cell there, corral, open bracket. As you see, you've got A2 colon A11. That's my first cell block. And I'm going to compare it against B2 to B11, my second cell block. So it's perfect correlation. Now look at data 1 and data 3. You can see as data 1 increases, data 3 decreases. And that's got a perfect negative correlation. And finally, as we see with data 4, the numbers do not change at all. Whereas data 1, it does increase, so therefore there's no correlation whatsoever, which gives us a value of 0. But in Excel, because it cannot give us this 0, we get the error mark. So now we're going to have a look at a correlation example. This exercise requires calculating the correlation between intelligence and the partners in a relationship. The table below contains test results ranking out of 30 the intelligence of couples in a relationship. And we need to see if there's a correlation between partner 1 and partner 2. And also we're going to rank for partners' intelligence between 1 and 6. Now we can see in this example the correlation command is very simple. Just highlight the cells, highlight the next cells we want to compare against. And this tells us that due to results being greater than 0.7, there is a correlation between this. But we need to be careful, because correlation does not imply causation. For example, we cannot say that dating intelligent people causes intelligence. Our next step now is to look at simple linear regression. Simple linear regression is quite straightforward, and it's very common use in data analysis. It is used to investigate an association between two variables, in other words, how one variable affects another. So, again, this is never text-heavy slide. I will be going through this slide in the next couple of slides using Excel. So first of all, we want to test if there's a relationship between sponge thickness and absorbance. We have conducted a test and we measured the sponge thickness as we can see in column A, and we had to look how much liquid it absorbed. Now, complex data to do the simple linear regression, we need to produce a graph. So what we do, we click the Insert tab, go to the chart, and we need a scatter graph. Our second part is to add in a trend line. So just right click on any button on the chart and then click our trend line as shown. Our next stage is using the menu, tick the boxes for the following: display equation on chart, display R² value on chart. Now we can see our equation at the top and also the R², which we'll be discussing later on. Y equals mx plus c. The equation represents a simple linear regression. So how can we use this in practice? Well, y represents our vertical axis, x our horizontal axis, c is the intercept where the straight line crosses a y-axis, and m is the value we multiply the x value by. So how will we put this into practice? If someone asked how much absorbency should we expect from a sponge that is 10 millimeters thick, we can provide the answer using y equals mx plus c. So we know that for every millimeter we expect 0.1392 milliliters to be absorbed. So we put 0.1392 times x plus 0.0668. So 0.1392 times 10, which is our millimetre thick sponge, plus 0.0668. So that provides us with an answer 1.4588 millilitres. So for a sponge that is 10 millimetres thick, we should expect it to absorb 1.4588 millimetres amount of liquid. So what is R squared? R squared is a measurement of a goodness of fit of linear regression. It gives a fraction between 0 and 1 and has no units. An R squared value of 0 means that knowing x does not help you predict y. There is no linear relationship. Whereas an R squared of 1, all points lie exactly on a straight line with no scatter. Knowing x lets you predict y perfectly. An R squared value of over 0.7 signifies a good fit. From a graph shown previously, we have seen that the regression model produced an R squared value of 0.9095. This means the model predicts the absorbent rate good enough for us to use the model. If we have an R squared below 0.6, we should question whether there is a relationship between the variables. Thank you. Additional material is available in these books and on our website. And I hope you'll join me for my next section next time.